Hi fellas and welcome back to the channel. In today's video, I am going to walk you through every single aspect of our line following robot, from the initial idea, the hardware we picked, the firmware we wrote, the problems that nearly broke us, and the final result. This is a complete breakdown. Let's get into it. So first, what is a waiter robot and why did we build one? The idea came from a very real problem in the restaurant industry. Labor costs are rising, contactlessly service become a priority after COVID. The small restaurants can't afford those fancy commercial robots that cost like a half a million rupees. So we asked ourselves, can we build something that actually works using components you can buy in any electronic market in Rawalpindi or Islamabad for under 10k? The answer is yes. And this is how we did it. Our robot does four things. It follows a black line track laid on the floor from the kitchen to the consumer table. It uses a camera module to detect which table it's at that stopped precisely at right one. It waits at the table for 5 seconds and then returns back to the kitchen when it's on. And if something blocks its path, a chair, a person foot, it stops and waits for the obstacle to clear. All of this is full autonomous. No remote control, no Wi-Fi command. The robot makes its own decision. We are a team of four. Muhammad Tayyib was our team lead that handled all the firmware. Abdullah Iqbal, me was the project manager that handled documentation and procurement and have done some parts of the hardware design. Maz Ali Khan handled all the electronic design, schematic and PCB, and Muhammad Salah was our integrator and tester responsible for making sure all the pieces actually work together. I will be presenting everything on the behalf of our group today. Before we build anything, we needed to ask, is it actually double? Is this actually double? Or this is on the technical side, yes. The main processing job is reading 5 IR sensor and the 5 IR sensor that are connected to the Atmega 328P or Arduino Nano Uno. But we have connected Arduino Nano afterwards. The table detection was done by ESP32-WROOM is also well within the module capability. All the components are available off the shelf locally. On the budget, our initial estimate was 6 to 8,000. We ended up spending 5,900. So yes, very feasible. Now, how does our robot compare to what's commercially available? The Canon T5 is one of the most common commercial restaurant delivery robot. It uses lidar and SLAM for navigation, which is incredibly impressive, but it costs over 5 lakh Pakistani rupees, way out of the reach of a small business. The bellboard of you have seen in it in the video, the cat-faced one, also use depth camera and SLAM that is also above 4 lakh rupees. But our robot 5,800 rupees and it works. Of course, we are not claiming to replace those robots. They can navigate around dynamic environment, carry multiple trays, and integrate the ordering system. Our follows a fixed track with a black tape. But for a small fixed layout restaurant environment, our approach is entirely valid, and the cost difference is enormous. We also reviewed the academic literature research like Ahmed et al. Showed the PIC-based line following on Atmega controller achieve tracking accuracy with plus minus 3 mm. Sharma and Gupta provide ESP32 cam can reliably detect the ARUCO markers to 80 cm and QVGA resolution. Those findings directly backed our design choice. Now, for the system architecture part, let me walk you through. how we integrated and connect all the pieces together. The brain of our robot was Arduino Uno, but sadly we burned one, so we have to use Arduino Nano at the spot. That's the microcontroller. Uh, it is the so now instead of Atmega 328P or Arduino Uno, our main brain was Arduino Nano. So the five IR sensor were connected to the our from our Arduino Nano, the L298 and motor driver which takes PWM signal from the Atmega and driver of the two geared motor, the HC-SR04 ultrasonic sensor pointed forward detected obstacle in the path, and the ESP cam vision coprocessor that run independently and communicate with the Atmega our UART serial. The ESP32 cam is interesting because it is essentially a small computer with a built-in camera. It continuously captures frames, looks for a table, markers in the image, and when it finds the target table marker, it sends a stop command to the Atmega over the serial line. The communication between the Atmega and ESP32 cam is UART at 9600 baud, simple, reliable, deterministic, no Wi-Fi overhead, no latency surprises. Power comes from a 7.4V 3-cell LiPo battery. The motor runs directly off the battery through the L298 and two separate LM-S7804 voltage regulator, bringing 5 watt to the logic circuit, one of the Atmega and sensor, one dedicated to the ESP32 cam. That dedicated regular was actually a lesson learned during testing, which I will get to you later. Moving toward the mechanical design. For the physical structure, we went for the differential drive configuration. Two DC geared motor on the rear axle, independently controlled with a single caster wheel at the front. Steering is done by varying the speed of the two motors relative to each other. If you spin the left motor slow, then the right, the robot turns left. Simple and effective. The chassis of the two-layer of 3 mm laser cut acrylic sheet. The lower layer holds the motors, the battery, and L298 and motor driver. The upper layer consists of the Arduino and serves as the tray platform 20 by 15 centimeter, which raise edges to keep the food from sliding off. Our dimensions are 28 centimeter long, 22 centimeter wide, and 15 centimeter tall, compact enough to navigate between restaurant table. We did a CAD design in SolidWorks and run a force analysis to verify the acrylic wouldn't flex or crack under load. The results show maximum displacement of 2.72 multiplied by 10 power minus 4 mm under a 400 kg payload. Essentially zero flex. Acrylic turned out to be the right call. It is light, easy to cut, cheap, and it is performed exactly as expected during the final drag run. Fastener are stainless M3 bolt and standoff. Motor mounting is directly drive to the rear axle with M3 bolt into the acrylic. Moving toward the electronic design, now let's get into the electronics. The IR sensor array. We used 5 TCRT 5000 reflective IR sensor arranged in a line across front of the robot. Each sensor has an IR LED emitter to photo transistor detector. When the sensor is over white floor, the IR reflects back strongly and output goes low. Over a black line, the reflection is observed and the output goes high. The 5 sensor give us a position reading. If sensor 1 is over the line, we are way to the right. If sensor 5 is over the line, we are way to the left. If sensor 3 is in the middle, we are perfectly centered. The detection range is 2 to 15 mm, which is perfect for reading 2 cm black tape at floor level. Now moving toward the motor driver. The L298N is a dual edge bridge driver. It accepts PWM signal on its enabled pin and direction signal on its input pins. We wire it to the Atmega's hardware PWM output timer 0 and timer 2. So the PWM frequency is hardware generated and does not eat CPU cycle. Maximum current is 2 ampere per channel, which is sufficient for our 6 watt 150 RPM geared motor. The HCSR04, the ultrasonic sensor, works by sending 40 kHz pulse and measuring the time for the echo to return. Distance equal time divided by 2 times the speed of sound. It measures for 2 cm to 4 meter with around 3 mm resolution, more than enough for detecting an obstacle in a restaurant corridor. The ESP32 cam. This is a module from AI Thinker with an OV2640 camera chip capable up to 2 megapixel. We run it at QQVGA 160 by 120 pixel, which is enough for detecting a table marker at close range and keep processing fast enough for real-time detection. The module has dual-core ESP32 silicon running at 250 MHz, so even at low resolution it processes frame quickly. Power supply design. One thing we learned the hard way, the ESP32 can draw up to 250 milliamp in a peak, especially during the camera capture. If you try to power the Atmega All5 sensor and buzzer and the ESP32 cam for a single LM7805, it overloads the thermal shutdown. We solved this by adding second dedicated LM780 with a heatsink just for the ESP32 cam. Total average current draw is about 1.05 ampere, which is 1000 milliamp LiPo that give us roughly 57 minutes of runtime per charge. The PCB was designed in Proteus and fabricated during the initial testing. We found a ground loop in the PCB routing that we caused erratic IR sensor reading that was resolved by rerouting the ground plane and adding decoupling capacitor near each sensor. But now moving toward the software design. This is where everything comes together. Let me walk you through the software on both controllers. Uh, Moving toward the Atmega, sorry, we haven't used Uno. We used Nano. We have imported the IR sensor library that reads the 5 sensor analog ADC channel and compute a weighted error value if only the center sensor sees the line is error is 0. If sensor shift left, error goes negative, right positive. Moving toward the motor library that takes a PWM value and dedicate command and set the L to 98 and output accordingly. Base speed is 150 RPM and the bit correction adds to or subtracts from each motor. Pit C implement a pit controller proportional integral derivative that convert the sensor error into a steering correction. KP, KI, and KD were turned experimentally. Ultrasonic library fired the HCSR04 trigger made the echo pulse with using the timer input capture and returned a distance in centimeters. UART-C handled a serial communication with ESP32 cam, and FSM is the finite state machine, the brain of the robot behavior. The state machine has 6 states. Int state powers on all peripheral initiated and motor start. Following robot is actively following the line. IR sensor are reading if an obstacle is detected under the 20 centimeter transition to obstacle state. Obstacle motor stop, robot wait if the distance clear above 25 centimeter, return to the following. Table detects. ESP32 send a UART message confirming the target table ID. The motor stops. Robot is centered at the table, transition to waiting. Robot waits at the table for 5 seconds. 5-second timer fires translation to returning. Motor reverse direction. Robot drives backward along the same track with the ESP32 cam detect the origin ID is equal to 0. Motor stop, transition to idle. idle robot wait at the kitchen for the next delivery command when a new target table ID is set. Transition back to the following. This is a complete delivery cycle, full autonomous, no human intervention. Once the delivery is initiated, ESP32 CAM firmware. The ESP32 CAM is programmed via Arduino IDE. Its job is simpler but critical. One critical issue we hit that ESP32 CAM was that we have used the new module of the ESP32 CAM instead of using just a camera and connected with its the connecting module. We have used the new ESP module that consists of a camera. Sadly, we were not able to program that ESP32 cam because we can't really integrate the libraries with that our ESP cam. Sadly, but we have tried a lot of time to make that ESP32 cam work, but we always get stuck into the library portion. So sadly, we can't make that part of our project run, but our LFR line following and our ultrasonic sensors were working correctly. Our voltage sensor and current sensor were working correctly and giving the accurate reading on the LCD that were needed, and that's it because we can't integrate the ESP32 cam, so we can't detect the table numbers or the table color. Now moving toward the simulation, we simulated our entire circuit in Proteus. We assembled before assembling hardware. This was genuinely one of the most valuable part of the development process. The motor speed differential response responded correctly to simulate IR sensor patterns. We used Proteus virtual potentiometer to simulate different line position and confirm the output. For the UART, we injected bytes directly into the Atmega RX pin via Proteus virtual terminal to simulate ESP32 CAM table ID message, the confirmation, and convert the FSM transition correctly. The HCSR04 was simulated using Proteus built-in the ultrasonic sensor model timing margin were verified with the Proteus digital oscilloscope. The one thing Proteus cannot do natively is simulate the ESP32 CAM's camera processing that was was always going to need real hardware testing, but simulating the UART communication and Atmega responses to recover that integration effectively. Total simulation time before touching hardware saved us probably 2 days of debugging. Now moving toward the testing phase. Once hardware was assembled, we give it to our group member to test it. So our robot placed on the 2 meter line and it followed the line without with the deviation of 5 millimeter that we consider as pass. Left and right cover tracking 90-degree curve section in both direction robot completed it. As I have told you above, our ES-Potato cam can't be programmed correctly, so we haven't detected any tables. But our IRU ultrasonic sensor was working correctly, and we have stopped it by placing a hand in front of it and returned to the kitchen. As I have told, we haven't programmed our ESP32 correctly, so the returning function of our robot was also not functioning properly. So that's the problems we have encountered a lot. The IR sensor, the one other notable problem that we encountered was the integration of our IR sensor. We have to integrate our IR sensor array so that it follows and basically we have adjusted its sensitivity so that our robot follows the black line correctly. But that was not the major issue. The major issue was of the ESP32 cam that we have failed to work on it. Now moving toward the budget and management. So our final bill of the material was 5,900. That is under 6,000. The Atmela was Nano was of 500. 32 cam was of 1000. IR sensor 600. L2 night at 300. 2 DC motor 700. 2 wheel and cost at 380. IR sensor 150. Batteries were of 1000 and acrylic sheet was 500 and PCB fabric PCB was another wire was almost 1500 compared to the 5 lakh for a commercial robot. We are at 1.2% of the commercial cost and we have fully functional prototype. That's wrong. We can say half functional prototype. For the project management standpoint, the project run over budget by 0 rupees and was delivered with 1 week of the planned timeline. The 1 week delay was especially the ESP32 cam issue, and it also didn't work correctly. So the lesson was that we have if we have should started at least a week before so that our ESP32 cam could work correctly. So now moving towards the lessons that we learned and things that can we can improvise on us so that our future work can be uh, polished a lot. Five key risk lessons for this project was always check whether your microcontroller programming interface shared pins with your runtime communication interface before finalizing the PCB. Never run a high current module like ESP32 cam on the same regulator. Test your IR sensor under the actual developing light condition. Add a 50% time buffer to any subsystem evolving module. Order long lead components ESP32 cam at least 1 week before you need them. So what we have to improve if we continued this project. Muhammad Tayyib's suggestion is to replace visual marker with the RFID tags for table detection, completely immune for lighting condition and access simpler firmware, and Wi-Fi based ordering management for a mobile app. Bluetooth cam has built-in Wi-Fi, so it's an addition. And for production use, replace the acrylic chassis with the aluminum for better durability and a buzzer alert when the food is delivered, and implement multi-tray version. So that's is a complete breakdown of our line forming robot hardware, electronic firmware simulation, testing problems and result. Now I will show you some videos of our working on this project. We have worked a lot on this project and we are very we are not happy that our project didn't work because we work a lot on this project, and I am also making this video with a heavy heart because we thought that we could complete our project on time, but we were unable to program the ESP32 cam properly. I am saying that again and again because I am very sad about that. So no worries. This is our learning phase, and I am hoping that we will solve this problem in the near future, and then we will work on this project and make it better. So if you found this useful, whether you are a student working on a similar project or just some curious about how autonomous robots are built, please like the video and subscribe. We are uploading more project counter on our channel. Another advice for our juniors or the video or someone who is watching this video to make the robot work, I will suggest you should use ESP32 cam that you will connect to the normal ESP32. You should not take the ESP32 module because it is very difficult to program, and also it is a new module, so a lot of its library is not available on Google or YouTube, and you will not find any related material for it. So it is easy to make your life easier and just use simple ESP32 cam attaches with ESP so that you can work on it. Thanks for watching. I am Abdullah Iqbal representing our group from a University Islamabad, Bachelor's in Mechatronics batch of 24, and goodbye.